Okay, so one of the really nice things about using two-level systems is that you can calculate everything exactly. And then you can also use perturbation theory to see what the result would be in that case. And then you can compare them directly and you can see when are they in agreement and when are they not in agreement. Right, so let's work that out. We worked out the transition probability in the last lecture segment using perturbation theory. And we found out that it was this in general for two states. The only thing we have to do is make the initial time t naught be 0. Okay, so we replaced the omega with omega kj because that f function was just in general. But we wanted to understand this function in detail because we're going to see this over and over again. All right, now if we convert this to the notation that we used when we did the two-level system, all right, well, then we had two levels, right? And we had this parameter delta, which was the energy gap function or energy gap value. So that would be like EK minus EJ, all right, which would be equal to h bar omega kj. Okay, and if you look back on your notes or derive it again for fun, then what you'll see is that we found in the two-level system, we could work out this exact same equation as we did before, right? The same thing, but now with no perturbation theory. But first, let me just put this notation into the same language that we had used before. So H primed was just our coupling, right? So this is going to be V squared, right? Then we have, notice what we have here, H bar squared omega kj squared. So if we square everything, the denominator of this is just delta squared, right? Because that's this here. Delta was just the energy gap between the two levels. We don't even know which one's greater. We don't know which energy level is higher. So it doesn't actually matter that much, does it? Now what we're going to do is we're going to put in omega jk, or omega kj, sorry. Remember, that's the energy difference. So we want to convert that back into an energy. So we can put that omega kj is equal to delta divided by h bar. So we can do 1 minus cosine. And this is going to be delta divided by h bar times t. Right? I'm just converting this equation back into the notation that we used for solving the two-level system, but exactly. Okay, what else can we do? So what we can do is we can take advantage of some trigonometric identities. Okay, so what would be that? What is a trigonometric identity? So we know that 1 minus cosine oscillates and it's above 0, right? So it's got to look, there's got to be a way to write that in terms of sine squared. The sine squared does the same thing. Okay, so it turns out if you work through all of that math, which if you like math, please do it for yourself. 2 times 1 minus cosine delta times t over h bar. Remember, delta, it's not delta t. Delta is the energy gap. T is time. This happens to be equal to 4 sine squared. We could have just written it this way instead. Delta times t divided by 2 times h bar. Now, hopefully that is somewhat reminiscent of what we had before. It shouldn't be too surprising. We're going to square sine, so we have to divide the frequency by 2. This was the frequency delta over h bar, you have a delta over h bar divided by 2. That's not surprising. Maybe the factor of 4 is not super obvious. Okay, so what can we do with this information is that we can just take the whole 2, 1 minus cosine stuff and replace it with this because they're equal to each other. So that gives us v squared divided by delta squared, okay, times 4 times sine squared delta t over 2 h bar. Now, you might ask yourself, is this the exact solution? Is this the exact answer? Right? And the answer is no, it's not the exact answer. There was extra terms. I would encourage you to go back and look either at the lecture segment or if you take notes, I don't know what people do. If you look in the Mukamel notes, this is also derived in there. All right. So it's not exactly the same. The exact probability to go from J to K with a constant field or a constant perturbation, whatever you want to call it, is actually very close though. It's 4 v squared divided by, again, 4v squared plus delta squared. Right? So that's our first difference right here. It's lacking that on the bottom. And then in the sine, we have sine squared, okay, fine. And then we had the Rabi frequency was not this. It was close though, right? It had the eigenvalue in there. Remember, 4 v squared plus delta squared, that square root, and then that times t over 2 h bar. Here we have just delta. But here, in the exact one, we have the square root. So what is this? When are these two equal to each other, or when do they start to get pretty close? We did this analysis before. When the coupling term V is very, very small, right? Then you can imagine that these two will approach each other. Because all we're doing is adding a v squared on the bottom, on the denominator. So if I have v squared and I'm adding some giant number, the field-free offset or energy gap, then surely I can ignore this. Right? That gets me closer to the perturbation theory result. If delta squared is much greater than 4v squared, then I can do this. Same thing here. If delta squared is much greater than 4v squared, I can ignore the term in the square root. And that gets me back exactly the time-dependent perturbation theory result that we derived. Right? And that is super important to see this, because it gives you a very quantitative meaning about what we mean by small, right? We mean, and of course we can take the square roots of all of these things, when the coupling parameter is much less than the energy gap that you have without, right? And that is basically one of the key lessons to learn from perturbation theory. And you can learn it directly when you have the ability to solve the problem analytically, using exact quantum mechanics and then using perturbation theory. So I think that's really cool. And it's really nice to flex the analytical muscles. You see the math, any high school kid in America could learn this, right? The math is not hard here. Of course, knowing what math to do is the hard part. All right, so we're going to stop, and then we're going to do the derivation of Fermi's golden rule, which is a very important thing. It has applications in chemical dynamics, but also, very importantly, for the spectroscopy context, for fluorescence and other spontaneous emission.